Hey everybody, how are we doing? Thank you so much. Kayla got married this weekend, so really big weekend. Got to see family. You know what? I'm gonna do a quick text to my parents because they're leaving. They're leaving as we speak. Thank you so much, Zachary. Got so many good questions in the chat already. They safe trip. Parents are leaving. And yeah, thank you so much, Madison and Brianna right there, and Colton. I appreciate it so much. Busy weekend. So quick times. Busy. Thank you so much, Kristen. I got the haircut last week. Really happy. Thank you to Gold Star Barbers, I think, here in College Station. Let's see that ring it. Oh, my ring's not the special ring. So it's just your usual ring. How does it feel? It feels great. This is our 10-year anniversary today. This is our 10 years of dating anniversary. So we picked, it was kind of, it's a hunk of a ring. I think I got it for like $100. Her ring's much nicer than mine. Her ring is got diamonds and all that good stuff. Yeah, I didn't get a, what's really funny is we did like a, toss of the bouquet to some girls who were there because it was a very small wedding. And the one girl said she was like, oh, she caught the bouquet. And then she asked her friend, she's like, oh, I'm just 19, I want to get married. And tells me I've been dating for 10 years. So she was 19 when we started dating. And now I'm old man. 8377. Welcome to, Kayla. Kayla, some HE double hockey sticks right there. Kayla, you're doing great. Making all the good food. Doing all for real, Brianna says right there. Brianna, you also married? When we get a Chelsea appearance, we're different. So Chelsea and I are we're a bit different. I'm loading up the homework here as we speak. And thank you so much, everyone, being here and all the positivity and all the support. Feels so great. It's really nice. And if you want, check out this post on LinkedIn. So let me share this link. I'm going to show you this link and copy link to post. Okay. So I'll put this LinkedIn post. This is, if you want to do something nice for me, you can just like this post right here. Does it work? Thank you so much, Parker. We're going to load up some questions here. So you can post on this. You can like it. Don't get me anything because I'm not allowed to get anything from students, but two, you don't need to. We had such a nice time with friends and family. And and if you saw the post right there, it's Dr. Kelly and I doing some presentation. Psychology experiment? You bet. Getting it loaded up right here. So thank you so much, everybody. We got psychology experiment coming up. So many great things. So if I'm a little frazzled today, I'm sorry. We're talking to our neighbor and he's getting married Friday. He was like, oh, did you guys just get married? And we're like, yeah. And he's like, oh, I'm getting married Friday. And we're like, wow. It's wedding season. Maybe someone else is getting married in the chat. If you're getting married, then chat, feel free to share that you're getting married. Let's see right here. Psychology rat experiment. I thought I saw another one or two. Let's see. We had psychology. Colton's wondering about, let me write these down and then so we'll make sure we don't miss any. So Colton wants number 3 on 475. So BAS 475. Question, let's say homework. Sure. Homework 7. Question 3. And we have Stat 201, Chapter 14, Rat Maze. And was there any others? Put those questions in the chat if you got them. Oh, that's all right, Brent. Well, don't worry. There's always room. Been married for almost 7 years. Congratulations, Kayla. That is absolutely awesome. Congratulations. Oh, we should do activity later today. I think we do. Got this. Do some activity. And let me see if I have meetings and stuff. We should do it later today, Kayla. That sounds great. Stat 201, Chapter 14. Put those questions in the chat if you got them. I'm taking them down as we speak. Flights. I think it's like flight delays or something. Okay, so let's see. Rat experiment first right here. That's towards the end of it, I think. Rat experiment. Let me open up jump. We're going to need jump. You want to use jump for this question. It makes it way easier. And you're about to see how easy some of these questions are with jump. So have jump ready to go. And I'll show you how to put questions in jump. Makes the question way easier. You're not ready for that? That's all right. Awesome. See you later, Kayla. Have a great day. And we're going to start here with some rat experiments on chapter 14. Let's check it out at 6:33. Here we go with rat experiments. Is more paid. That's awesome. Shouts to Kayla's husband right there. You're awesome. Here we go. Right now. Okay, so we're doing the rat experiments right here. And with this, have jump loaded up. Do not do this problem by hand. It's way more difficult by hand, takes way more time, and it doesn't really mimic what we'd be doing on the test if you solve things by hand by solving the meanest standard deviation. You're given data on rats, so this is just a column of information. You have the time it took the rats to go through the maze, and they want to see if it took 60 seconds or not. That's awesome right there. Shouts. We love it. So we're going to copy to clipboard. Control-C, Control-V, and now have jump open, and with jump open, you want to go to File, New, Data Table. I'll pause right there. Oh, thank you, Kayla's husband. So, File, New, Data Table. Now, don't click inside of it. You already probably clicked inside of it. I should have told you not to click inside of it. If you already clicked inside of it, you can hit Control-N or Command-N to open a new one. Don't click inside of it, though. Don't do it. A lot of people just click, like, ah. Now, what you'll notice is time was actually in the column space. If you notice right here, when you do this, time is up here in the column space. You need to make sure when you're over here, you go to Edit, Paste with column names. Number 8 on Canvas content. Oh, check that out. Yeah, Briley, we'll do that here in a bit. You bet, Briley. Great question. So paste with column names, and you have it. Now, here's an important thing. Can anyone explain for 1,000 points why this won't work? This is a very common error when doing this. We're seeing the errors that can occur. This person did not paste with column names. Right now, Jump thinks their data is what? Because the column name went in first in the first row. So they did not paste with column names. Restart if you have this happen. Don't try to fix it. Just open a new sheet. But what has happened for 1,000 points right here? Jump thinks their data is what currently? Because that person did not paste with column names. You have to go to Edit, Paste with column names. Probably the most common error. You might be like being like, oh, right now you might go, oh, totally, that's me. Very common error that I have. So I try to show the common errors as we do this. Right now, Jump thinks this is what kind of data? Look at the blue versus the red. If you don't paste with column names, it's going to think that your data is what? Don't try to fix it. Just open a new sheet and paste with column names. File, New, Data Table. Oh, does no one know? Oh, no. Jumps thinks it's the other variable type. Jumps doesn't think it's quantitative now. It thinks in this sheet that you're dealing with what kind of data, which won't analyze the way we want it to. Jump thinks your data is... What's Jump think the data is? I'll drink some more coffee. Then we'll answer it. Jump thinks the data is... I'm on Top Chat. Jump thinks the data is categorical. Notice the red right here. If you have this and you're analyzing quantitative data, it won't work. Once again, don't try to fix it. Open a new sheet and paste with column names. I'm not even on a new sheet over here. You want to open a new sheet and then paste with column names inside of it. Go to Edit and then paste with column names. I don't have the paste in there, but you'll have this over here. So make sure to follow those steps and make sure to achieve what looks like this. With this achieved, we can now analyze the data. Don't use this right here. This is bad. So now it says make a 95% confidence interval, and life is easy on this because in Jump, we can go to Analyze Distribution. This is Analyze Distribution. We'll show it here on the close-in. Analyze Distribution. This will analyze a univariate quantitative display of data. So when we go to Analyze Distribution, we can just double-click the Y variable of interest and then click OK. So now that we have the Y variable of interest in there, we can look at the distribution of times that the rats took. Now, your distribution might not look exactly like theirs down here. I promise it is, though. Go to the stack. So we're clicking the red arrow. Pause for a moment. Now that you've clicked the red arrow and clicked stack, you'll see it's in horizontal layout. It still might not look exactly like these down below, but look at the scale. 20 to 100 in units of 5. So we're going to double click right here, and we're going to go 20 to 100 in increments of 5. Hopefully I didn't click the wrong button. I think we've done it. There we go. So you might be able to figure it out elsewise, but we have a big outlier rat over here and then the other remaining rats down here, and you can see it. And I double clicked this and I changed the units 20 to 100 by units of 5, and that changes the scale and makes the histogram look like this. So the answer for the histogram is over here. Now remember, we needed that 95% confidence interval, And the 95% confidence interval is right over here, 46.27 to 59.02. Try interpreting this. I am 95% confident that the true mean time it takes for rats to run the maze is contained in the interval 46.27 to 59.02. So let's go right here. 46.27. Oh my gosh. And then let's grab the other number, 59.02. This is what we're trying to understand, the actual time it takes for rats to run the maze. And now we want to know if it looks normal. Yeah, chocolate chip question. You bet, Casey. Mubot saying hey in the chat right there. Thank you, Mubot, being so kind to everybody. Flight, we can do flights and chocolate chips. You got it. I'll put those on the list. You got it. We'll do a few more 2-1s, then we'll do some 475. So stay tuned, 475 and 320. If you got questions, let me know. Now, with this right here, he'll keep saying hi if you say hi. He'll be in an infinite loop. Thank you. He's my greeter these days. I just want to make sure everyone's always feeling welcome here. When you do a normal probability plot, normal probability plots are going to be more straight if they follow the normal. The yogurt question, you bet. I think we'll have just enough time. Got a lot to do. So keep answering questions. When is a normal probability plot normal? The more normal it is in hot dogs, you bet. I'm going to take these all down here in a moment. You bet, Zach. When is a normal probability plot normal? When does a normal probability plot look normal? When does a normal probability plot look normal? When does a normal probability plot look normal? Here it is. That's a normal probability plot. When it's straight, exactly. It's kind of like straight enough. The more straight it is, the more normal it is. And the way to tell this one pretty quickly is, do you see this very high point up here? If we zoom in on this one, do you see this point up here that's like 90 or 80 something? That's the observed value. So this is the very high observed value in our data set. And if you go over to our data set, you can see that very high observed value right here, this 93. You can make the normal probability plot in JUMP by going here, by going to normal quantile plot. I'll pause on the screen right here. Now, the more straight it is, the more normal it is. JUMP plots it similarly, but not exactly. That gets me a little bit about the way my Pearson shows it. But that point is way off the screen right here. JUMP plots it pretty similarly, but notice how there's this high outlier here on the high side. So it's mostly straight except for a high outlier. Does that make sense? Mostly straight except for the high outlier. Do you see how this is mostly normal except for a high outlier? Try to connect the ideas that this is mostly normal, mostly straight except for the high outlier. The more it follows this line, the more normal it is. So this is pretty normal except for this high point up here, which deviates from normality. So that's what the normal probability plot is showing us. And we see mostly normal right here except for a deviation on the high side. And notice how that is up there in the 90s. So that's the normal probability plot, a plot that shows us the probability the curve is normal. So for the conditions, dun, 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 random, it doesn't mention 10%, come on. And then it's going to talk about the outlier. The histogram is the histogram is roughly unimodal with no outliers. No. Normal probability plot is relatively straight with one outlier. Without the outlier, the conditions seem to be met. The histogram is roughly unimodal and symmetric with no outliers. I think we're good on this. A little scared on this one. The randomization is met, the normal probability plot. So what is the third condition right here? What is the name of the third condition that they're not telling you? That would be very important to know for the test. Condition 1, randomly sample observations. Condition 2, less than 10% of this population of rats would be sampled. So probably less than 10% of rat times, because there's pretty much infinite rats with infinite times that could be sampled. So we're good on 10%. Probably why they don't mention it. And condition 3 is what? What is the name of condition 3 that they're talking about right here? They're talking about it and checking it, but they don't call it by name. What is the name of condition 3? Are you actually brother, sister? That's crazy. What is the name of condition 3? What is the name? Condition 1, randomization. Condition 2, 10%. Now pause. And what is the name of condition 3? We're seeing how long does it take for rats to run the maze? Pretty much, Kristen, pretty much. That's a part of the condition. Today or from now on, we'll be calling it the large enough, excuse me, I just said the same thing. We'll be calling it the nearly normal condition. We'll be calling it the nearly normal condition. So from now on, we'll be calling it the nearly normal. Sophia, yep, we're going over now. Good stuff. The nearly normal. And we can check it by looking at the histogram. Madison, 500 points. No, that's all right. It's good practice also to you, Kristen, the points too. It's good practice. So like when you do, you're like, oh yeah, now it's called nearly normal, which we can check with things like the large enough n. That's one way to check it. So we have look at the histogram, look at the normal probability plot, look at the p-value, 3 ways to check it on the screen currently. And they're kind of alluding to that with the normal probability plot right here, saying it's relatively straight. So they're doing a check via normal probability plot. Now, when you get down here, it says eliminate the outlier and redo the interval. Now, here's a trick inside of Jump to make this super easy. What you can do in Jump and watch these steps. So I'll try to do it slowly and watch these steps. We're going to go right here to our data and go to the top button and go to redo and go to automatic recalc. So check this button right here, redo automatic recalc. This means if we make any changes, it'll automatically redo the data right here. So we're going to click the automatic recalc. Boop, it's now clicked. And then we're going to highlight this 1 point. Does everyone notice how that, you can even click it down there. We're highlighting that 1 point. Now that you've highlighted the 1 point, whether you click it or whatever, make sure it's clicked. Click it, pop it, twist it, whatever you want to do. Just make sure it's highlighted. And now go to rows, hide and exclude. Now keep your eyes on these numbers. Since we have automatic recalc on, make sure automatic recalc is on. If automatic recalc is on, did I just click the wrong button? Oh no. Hide and exclude. You ready? Now look at it. Great job right there. Kristen got it. We now have automatically recalculated this. So it just redoes your results for you like that because it just automatically recalculates them. It just says, oh, you want that point removed? Here's your results without it. So we removed that observation. And now we have a new interval over here on the side with that point removed. So it goes from 45.59. Watch me get one wrong. My brain is booting up with this cup of coffee number 2 to 55.64. Please tell me if I got a decimal wrong. 2 decimals. Does the rat maze meet the requirement that it takes at least a minute? So they want it to take at least a minute for the rats to go through. The maze does not meet the 1 minute requirement. Both confidence intervals are entirely below. There we go. Does not meet it. Both intervals are completely below. That's below, and the other intervals below. I don't think I've misclicked. Let's just say not today, my Pearson. Here we go. Not today, my Pearson. Not today. Good question. Good theory. Let's head back. We're going to do 2 more stats to 1. Then we're going to do a 475. But don't leave stats to 1 when we do some 475 because we'll come back and do more 201. Okay, we got lots of questions. Please put all those. Let me make sure. We got flights coming up next. I saw hot dogs. So we got chapter 14, hot dogs. About the bags of cookies. We got cookies. What else we got? We got cookies. We got flights. We got hot dogs. We got cookies. What else? We got the 1,000 chip trial. Let me see if I see the other ones. Flight destinations. We have that one. Yogurt. We got some yogurt. Yogurt. What else? We got flights. We got cookies. We got yogurt. Yogurt. There we go. We'll do yogurt after flights, and I'm gonna put the chapter 7. Okay. Let's go find flights, then yogurt, then hot dogs, then cookies. I'm gonna put the cookies after. It's like we're having a buffet right here. This was our wedding platter. It was cookies, yogurts, and hot dogs. It was actually tacos, because tacos rule. Yeah, everyone knows tacos rule. Could you help with 475? Month column to change to a numeric? Uh-huh. You bet, Carter. Got the... So, and which one is that? Which portion? Just wanting to change months to a numeric? Look at that. Message me on Discord, too. That one's fun. Is number 1? Look at number 1 here. That's what I thought. I was trying to remember which one it was. My brain's been in... We're going to look at some flight data here. This one's good. This one's a very good test question. Here with flight data, we'll look at question 1. So let's do question 1 and question 3 when we do some 475. Here we go. Got it listed. Okay, we got flight data ready to go. Everyone, thank you for such a great day. Let's hop into this. Here we go. Flight data. Okay, so one of the reasons this question is great for the test, you use mutate. Exactly. Okay, we're Colton. Just pipe it through mutate. And so with this right here, what we have is we have summary statistics already. They sampled 72 flights. The average for the, I think its delay was 80.69 with a standard deviation. Great function right there. And then the standard deviation was 2.74. So we can just read through this and understand what this table is. From this, we need to create 95% confidence rolls. So, or what percent? Something like 95%. We'll find out. Okay, we're going to copy the data. And then I'm going here to Word document from today's. Oh my gosh. There it is. And the conditions are the first thing we need to check. Okay, help me out. We know this so well. Condition 1, help me out, stats tool 1. If you're here and practicing, you just know when you get to test, you get to condition 1. What is it? Chance for me to relax right there. Random, Leo. Great job, Leo. We were talking about you this morning, saying how awesome you are. And everyone here is awesome. Kristen, thank you so much. Kristen and Leo, you guys both, I say guys for everybody. And Madison, too, just leading the way. We're throwing out an extra 500 points. Just being here practicing, it becomes second nature. When you get to the test, you're like, random, 10%. And then the third condition is based on the data. And so, Kristen, what is the third condition? Since we're dealing with quantitative, what will the third condition be? They break it up into independence, random. That's just random. There you go. They're just breaking that apart. Random and independence. Tomato, tomato. They're breaking it apart. Nearly normal, another 100 points, Kristen, right there. We love some stats. Exactly. Kristen, let's throw out some 500 points your way. It was excellent, Leo. Excellent, excellent, excellent. I'm wearing a ring right now. I'm wearing a ring. Sure. Why would you say the nearly normal's met? This is 72. Exactly, Kristen, right here. It's like the number one way. And why would you say this is nearly normal? Remember, we're looking at the percent on time, and we're collecting it from monthly data, so this is actually a quantitative response. It sounds kind of proportion-y, but we're looking at, I think, like monthly, like percent on time. I don't think I get it. Bling Bling Boy? Tell me what it's from, because maybe I don't get it. I don't know if I get that reference. I make a ton of references, as you see. What is that from? Oh gosh, Brian's getting old. And why would you say that's nearly normal? One of the ways to check nearly normal is to simply look at the histogram. So that's the way over there, is just look at the histogram and be like, yeah, it's pretty normal. Johnny Test? Oh, I watched Jimmy Neutron. Jimmy Neutron, was that Cartoon Network? Old Chelsea. Jimmy Neutron was a little bit after my time. God, I hate saying stuff like that. I watched like Codename Kids Next Door, Courage the Cowardly Dog, Ed and Eddie, of course. But Cartoon Network, some good stuff right there. Yeah, probably just a little bit too old. Yeah, you're right. Jimmy Neutron was Nickelodeon, and I watched it with Chelsea afterwards because I was a little bit too old for Jimmy Neutron too. Codename Kid Next Door is really great right there. Like, that's a great show. And Courage the Cowardly Dog. Oh, it's from the same era as those? Oh, darn. And Johnny Bravo. I say Johnny, like Johnny Bravo. Whoa, mama. Courage is the best. Courage is great. Courage is such a weird show. Oh, and The Grim Adventures of Billy and Mandy. So we know it's pretty normal because it looks normal. It's like we look at it and say, it's pretty normal. Oh, that's cool. You dressed up as number 3? That's so cool. I should shave my head and dress up as number 1. Was he number 1? I think he was, right? It really was the best era of Cartoon Network. It really was. Now, this is where the question gets tough. You ready? Here's where the question gets tough. The question gets tough. They should have had number 0. There might have been an episode where they had that, like someone beyond number 1. There was, because there was like different like places. Anyways, I'll try to focus. Did you see Courage was in Scooby-Doo? Ooh. Oh, don't worry, Kristen. Don't worry. You're stuff from my college life. You guys grew up with it like in like your lower school and stuff. This is my college life. I watch cartoons all the time. I just don't watch enough these days. I watch more anime now. That's the adult cartoon. This is where people usually get stuck on this question, or where the errors occur. I'm going to focus. The errors occur on this question because to make this, we need the following equation filled out, and I'll show you where people make mistakes. We should notice the notation we have is we have a sample mean, and we're going to use the equation with plus or minus a t with n minus 1 degrees of freedom, star meaning based on the confidence level, s over square root of n. So now I need your help. Oh, Fairly Odd Parents. So where do you think people usually make mistakes? Where do you think it goes haywire? We didn't even mention Kim Possible. That's Disney. Some Ron Stoppable. Wilfredell. Batman Beyond. I'm going to stop. T with n minus 1 degrees of freedom. So that is basically the Z. And that's where people usually get stuck. So now we need to go to the T applet. Yep, that's the error usually. And so we need to go to the T applet. And on the T applet, we need to say we are building a 90% confidence interval. So we're going to go here to the in-between and go to 90%. Now you notice that shades the middle 90%. And then Kristen also said, Kristen, great job right there. We need the degrees of freedom. What are the degrees of freedom for this problem? The T is going to be like 1.67 probably. What are the degrees of freedom for this problem? So how do you know degrees of freedom and what are they for this problem? So the degrees of freedom, that's a DF, is the n minus 1. That's the thing down here. So the degrees of freedom are this. That's what they are. Can you explain the difference in... So it's always plus or minus. It's all... Oh, so the other ones we use for testing, Leo, like the less than, the greater than, or the does not equals. So this one I use for confidence intervals, and the degrees of freedom for this will be 71. So when we do testing with the T, which we're kind of getting to at the end of today, you'll do things like the less than, the greater than, or the two-tailed test. This is the one I use for confidence intervals. This is the less than test, the greater than test, the does not equals, and I don't use that one for graphing. It just exists. So we need the 71 degrees of freedom, and we need 90% confidence. What have I done to this? I think it's not showing properly. There we go. I said about 1.67, and that's accurate right there. 1.667, and you can see it right here. It doesn't matter, Rock knows. It doesn't matter if you use plus or minus, because we will do the plus or minus on it, and everything over here is the margin of error. Does that make sense? And all Shazad, great answer. All the assumptions are met. I'm 99% certain because it looks pretty normal. We've randomly taken these flights that are less than 10% of all flights, random 10%, and nearly normal. Shazad, great answers. And so, and now, 80.6944 plus or minus 1.667, 2.74348 over square root. Why do they give? Why are there so many decimals? Why? Why decimals? Why? Why so many decimals? 2 points. Oh no, we got to do square root of 72 first. 72 square root. There it is. 2 point. They really want to be accurate on this. There we go. Okay, that is the standard error. Times that by 1.667. That's the margin of error. So now we can rewrite the interval as... And this is the margin of error right here. Oh, how did we get... Shazad, good question right there. I'll show again. So you have to go to the T applet. Yeah, exactly. And the decimals are pretty nut crazy on these. Where is it at? You have to go to the T applet, Shazad, and you have to put in your degrees of freedom, and then you have to shade the middle percent that you're talking about. So the T applet, I'm going to put it again on the screen right here for you to see. Go to this link right here, go to the T applet, and you'll be getting the T value for the percent confidence. Make sure to do the between. Put in your percent confidence, put in your degrees freedom. So it's like 3 steps. What's your confidence level? Like 95% confidence. This question doesn't ask that though. It says 90%. Then make sure your degrees of freedom are in here. When you change this, I do think it changes. Just be careful. Make sure it doesn't. Sometimes it changes values, but make sure it still says like 90 up here. And then make sure you're shading between. Just make sure it has those values. And that's probably where most people get stuck on this, because that's the big solve of this. And so now we're just taking those values. Here we go. I can't remember not to shake it. It'll get mad at me. And we're just going to add and subtract those. Okay, so let's add and subtract. 80.6944 plus, there's that, 81.23. And then we go right here, 80.6944 minus 80.16. Just make sure to carry decimals. It is very particular, but that should do it. Choose the correct answer. I am 90% confident that the euro contains the true monthly percentage of departure times not on time. Boo! Woo, Leo, I got a little bit scared. Everyone know, like, a few people have been using tables. I don't use tables. I don't like them. A lot of times if you do the help me solve this, it'll have you use a table. I'm not a big fan of that because you can just go to the applet and get the exact T statistic. Tables are what people used to use 15, 20 years ago. Just a lot of programs and teachers haven't caught up to that. We have it. Nice job right there. I'm sure Kristen will do it still. Kristen, great job right there. Everyone's texting away right here about the travels. Do the yogurt one. Yeah, the question about the company testing you. Oh, I see Jacqueline right there is ready for it. We'll head back to the main screen and do more questions. Here we go. I want to give a huge thank you and shout out to everyone in the chat. Definitely helps out. I used to be a lot smaller on the screen. I don't know why I did that. It's so much stuff. We got one more 201. Then we're doing some 475. Then we'll come back to more 201. Huge shout outs. We're going to try to go pretty much even long today. We're going to do the yogurt one next. That was on the docket. So say thank you to Kristen right there. We haven't done the local downtown one. Hot dogs question. I was telling my parents I do a New York accent so much. They're from New York. My dad is from Rochester. My mom's from the Bronx. I don't know if those what accents sound like in those areas. My apologies to anyone from Bronx or Rochester. But I think Kristen noticed the similarity between the rat race question. Did you notice that, Kristen? You're like, ooh, I bet I could do this one with jump. So we're about to do the yogurt question, which is a jump type question. And I did indeed. Kristen, another 100 points. Keep it up. That's what I want people to be like, oh, wait a minute. This one's like the other one. Then you can solve it. Let's go ahead and check out the yogurt question. Here we go. Exactly. This question right here is going to be way easier with jump. We might even be able to speed run it. So what we're going to do is we're going to go to File. Here, I'll zoom in so you can see it. But you can't see that. John Cena. File, New, Data Table. File, New, Data Table. File, New, Data Table. It just does not want me to show you it. File, New, Data Table. There you go. File, New, Data Table. If the confidence interval is larger, would the margin of error be... Sounds to me margin of error is larger. That, with what's written right there, Brianna, it sounds like it's going to be a larger margin of error. Larger confidence interval is probably... Like, if the margin of error gets larger, confidence interval gets larger. Usually it'd be phrased the other way, like larger margin of error is larger confidence interval. So we're going to take that data. Now, be careful when you do this. Don't click inside there. Great job, Kristen and Leo, practicing. Copy to clipboard. So we're just copying the data. Now we're going to hit Control-C. And here's where you have to be careful. Is now there's no column name in this one. They just like to be weird here. So there's no column name. There's no column name. The reason I mention that is because when you paste inside of a new data sheet, you can either paste with column names or paste. There is no column names on this one. We're just regular pasting right here. If we pasted with column names, then the first observation would go into the column names, creating an error. So paste normally. Exactly. There's no column names, so don't paste with column names. Great job, Leo, right there. Just normal paste. And this makes our life easier because using jump, we can go ahead and go to Analyze Distribution. With Analyze Distribution, we're looking at one variable, just a quantitative distribution, because this is how many calories in the yogurt. And we're going to double click it. Boop, boop. And with this right here, once we click OK, it's going to do most of the work for us. Sound effects. And now we're going to click to the top right arrow, and we're going to click to stack. This just makes it look pretty right here. Now that we've clicked stack, it'll be in horizontal layout. And let's go look at this. Now, if you notice the number line down here, it goes from 80 to 200 in units of 20. 80, 200, units of 20 going up, because 80, 100, 120. And we almost have it. We just need to double click the bar, click, and then we're going to go starting at 80 to 200, and the units are correct. Now that we've done this right here, here's what it looks like. Well, that's weird. Oh, ain't that weird? Did I make a mistake? Oh, the units are wrong. Why is it? Let me do this. Well, there we go. Well, that was weird. It is C. Great job, Jacqueline. 500 points. Jacqueline got the answer before I did. The Binwitz, was it the Binwitz was off, Leo? How did I miss that? Leo right there seeing Binwitz. Where's Binwitz on here? Why do I not say Binwitz? I've been doing too much. I changed the minor tick right here. If you look, I need to change that. I removed the minor ticks to 0, and that looks to have done it. Yeah, there's the bin increments. So it put like an extra separation in there, causing issues on the way it visualized it. Jacqueline, great work right there, finding answer C. It is answer C right there, and you can kind of see where there's this kind of peak of data right here, those observations right there. So great work. That's just, we could put a count access. We don't have to, but we could if we want. Count access. There's like what? There's 4 observations right there. You can hover and you can see it. There we go, 4 observations. So with this, we now have most of the information we need. It is answer C. And now we need to look at a normal probability plot. Now, the way normal probability plots look is if it follows a straight line, it's good. If it doesn't follow a straight line, it's bad. I want you to think of it this way. Is this histogram right here mostly normal or mostly not normal? What is this histogram? Kristen, message me it. Then probably the number line wasn't entered in exactly, and you might want to look at the data. Well, what should normal look like? Unimodal and symmetric, right? Now, I know it's not perfect. But I'd say it looks kind of good. It does have a little bit of bimodality, which actually I think we can kind of see if we look really closely at this. I'm pretty sure this is the one. Let me see which one it is. I think this is the one right here. And with this, Leo, whoops, we need to click answer C. The highest point in this data set is 151, 154, 158, and 164. Do you see these 4 points right here? This 164, 158, 154, 150. It's slightly normal. And look at these values that are in the 150s. Do you see right over here? These are the 151, 152, 154, and the 160 something. These 4 values where Leo is seeing that second modality, that's what Leo is seeing over here with that 151, 154, 164, and 158. That's those values, 151, 154, 158. If you trace over to the left, you can see the actual value. So that's that little modal area you see right here, Leo, and that's that modal area here. And then there's a low value right here in the low 80s, and we should see that, and that's that value right there. So you should be able to trace over and kind of see the values. Does that make sense? If you're looking at this properly, you will see the values right here, and it'll generally follow a line or not follow a line like bend. But you see there's kind of this modal area, which Leo is seeing. We can't see the histogram up there anymore, but this was one modal area Leo is seeing, and that's the other modal area. I'd say it's mostly normal. But remember, you trace to the left to look at the numbers. So if you want to see what the number is right here for this is where 88 is at, and that confirms it's this point right here at 88. You can also have Jump do it. Jump does it similar-esque. You can go right here to the normal quantile plot. I'll pause right there for a moment. And you can see that there are the 2 modal areas we are seeing with this modal area here, this modal area here. And just look at that. That might help make more sense. There's modal area Leo was noticing there. There's modal area Leo was noticing there. And there's the low outlier down there at 88. So might help to see this also. But you should see 2 modal areas, and it should be mostly linear. And that's what we see with the following graphic right here. It always goes up to, so this one's wrong because the data, this would have a huge gap in the data from like 118 to that point. There's no data between 118. Does that make sense? Who's following me that if this was the right answer, there'd be a huge gap where there's like 120 and then there's no data till about like 160. There's no data in this range right here. There's no points. So these are the observed values over here on the left. So you would have 120 and then 160, but you don't see that. You see values over here. Good. Yeah, just making sure the graphics make sense. The biggest thing to know about this is that if the normal probability plot is straight, it's normal. That's the big thing we've been reviewing about normal probability plots. It's a one way to check the nearly normal condition. Are the assumptions met? Woo! Okay, let's see. It's relatively straight. Relatively. It's random. It's relatively straight. Oh, Leo, I might get this one wrong. Let's take a big breath right here. Okay. The randomization condition is met. The normal probability plot is relatively straight, and the histogram is roughly unimodal and symmetric. So, that, yeah, it's with a lot of these conditions, you're usually looking to pass them. So we're like, it's good enough. It's good enough. It's close enough. On the test, we'll make it very clear if it's bad. If it's bad, we'll try to do something ridiculous. I'll show you one of those in a moment. But the 95% confidence interval is the easy part. If you've been following along, you have that answer right here, 113.54. It's that lower bound right there. And then the upper bound is 145.55. The diet claims that it's going to be get an average 130 calories from a serving of yogurt. Do you believe that? Why or why not? Does this interval support the claim or not support the claim? The confidence interval, does it contain it? Well, it does. We got a lot to do, so I'm going to give the answer. The confidence interval contains the claim at 130, so the claim is supported by the interval. Oh my gosh, we got another 100. We're rocking and rolling today. If you had something that failed a condition, let me see right here. I can show you. I'm opening R real quick. Something, because people might say, like, what does a bad normal probability plot look like? And I'm going to show you those really quickly at the end of this question. R's taking a while to load. We'll show bad and good normal probability plots, and that'll lead into us doing some 475. So good and bad normal probability plots. If you had a good normal probability plot, all of these normal probability plots here are good. All of these are good. Why are these good? Can anyone explain why these are all good? These are all good normal probability plots. Like everyone I'm showing right here is good. These are all good. Every one of these, because they're generated from normals, that's kind of theoretically why. But why visually are these good? Some might look a little weird, but these are all actually normal. They do come from normal data. So why are these all good? These would all be good, and these are like great test ones right here that if we just show you one of these, even if it looks a little weird. Awesome. Let me look at that next here, Kristen. In between the segments, you got it. Even this one, you might say, it's got a problem over here. And you say, it's mostly linear. Goodness of fit. And you could do the goodness of fit on this, Leo. The goodness of fit should come back with a p-value above 0.05. It's going to do random other numbers. But the goodness of fit comes out with a p-value above 0.05. And so that means it's probably normal. It's what we saw was likely. Now you can change this and see the other side of it where you have a not normal data set. So we'll show the histogram of this too. The histogram, these are the three ways that we talk about in 201. Way number one is to look at the histogram, and the histogram looks unimodal symmetric. Shoppers, you bet, Sally. And then it looks mostly straight, and then the p-value is above 0.05. Now this is not normal. When it's not normal, the histogram won't look unimodal symmetric. The QQ plot will not look straight, and the p-value will be below 0.05. If you notice right here, this p-value is basically 0. That's scientific notation for something like, I'm doing it very quickly, something about that. That's not quite it, but it's, there we go. That's scientific notation for that. So that is a basically 0 p-value telling us that this is very unlikely given the data is normal, i.e. reject normality, and we have evidence of non-normality. So those are the three ways to do the nearly normal condition, and then there's large enough n, which is the sample size large enough, then we're good. Back to the main screen, here we go. Okay, we're taking a quick break from 201 to do some 475. We got shoppers downtown. Okay. We'll do a little 475. How's everyone doing today? It is a busy day already. $475. Assignments are hopefully going to get graded. Where's that assignment? Assignments. Cumulative, love it. On April 29th. Good breakdown. Studying for an Excel class. Awesome stuff. Let's start a little 475 here. Let's put this on the screen. It is 45 and 48. Here we go to the main screen. Let's do it. Some activity. We'll probably do the full activity later, Lillian. So would it be okay if we did that later, Lillian? Let me know, because we'll probably do the full activity, everything completely. Paper due tonight. You got this. You got this, Kristen. You got it. So we'll look right here. We're bringing in some data. I love it. I love the way that Adam Spanmar incorporates a lot of ideas. This is actually reading in a URL right here from online. and take a look right here. We have where's it being read on? Spreadsheets right there, bringing in a Google Doc right there, reading in an HTML. So this is why we love coding, because you can just take data straight from the internet. Might even go, we can see what the data fully looks like. There it is right here. So we have monthly hotel data right here, and then we need to turn it into a TISBL. So we've got the rooms, the revenue, good stuff right here, maybe from a major hotel chain right here. If a hotel books 1 room for 2 days, that's 2 nights. If a hotel books 10 rooms for 2 days, that's 20 nights. Good stuff. Monthly data to hotels, motels, and guest visits in Victoria. First column, total numbers, exactly all this good stuff right here. So we got hotel bookings. I love it, author me. So when we look at this right here, what we need to do is turn this into a TISBL. What is a TISBL? Technology, part A, and do some the technology one. You got it, Sophia. What is a TISBL? So a tibble is a special kind of table in the tidyverse. But what does TISBL stand for? The TS of the TISBL. So it's going to change the class of an object. If you're wondering, if you're watching from 201 right now, class is how something is seen inside of R. Like class here is of 8 is numeric, but class of like Brian says string. And that's actually something we were dealing with inside of Jump, because Jump even looks at the class of an object to see how to handle it. Because programs need to be like, well, what is this? This is a numeric vector. So inside of R, we could have a numeric vector, something like, here's a vector of numbers. And then when I take that vector of numbers, I could say mean of it. And whoops, I don't even know what I clicked. There we go. I could say mean of it, and I can get the mean of that vector. So you have to make sure. Awesome. Have fun, Kristen. Enjoy. So we have to make sure this has the right class or the right way the computer sees it. So we need to tell it to see this thing as a TISBL. Right now, let's look at it. Hotels right now is being seen probably as a data frame. It's a data frame. Data frame is like what we usually have inside of R, our Jump. A data frame is this right here. Here's a data frame. We are making a data frame by doing this. This is a data frame. It's just a data sheet. And if you look at your hotels data, it looks just like that. Yeah. Oh, we should do Canvas content next. Thank you, Briley. I'm going to put that next on the list. Briley, your Canvas content, you got it next here. So let me say Canvas content. Awesome. And then technology. Good stuff. We're doing that here later. Anola, great thing. Thank you for asking. We'll do that after 201 today. So stay tuned. I'll post the video next and you'll see it in that. And if you don't see it, but swing by for it and we'll do some 320 activity 10 help coming up here a little bit later. So if you look at this, we need to change what the class of this object is. Remember, the class of an object is how it sees it. So when we talk about changing it to a TISBL, let's see what we got right here. Well, first off, you're welcome, Anola. We're going to go as TISBL. Oh no, we haven't even loaded up our library. It's probably earlier, but I'm going to load it up right here. Libraries are basically a bunch of tools and functions and data sets. We're just opening up the world to us here by opening up a library. Library just gives us a lot of options because when I typed as TISBL, it didn't show up. And notice that's in the Fable library. For some reason, an image is missing. So what are we turning into a TISBL? The X is what we're turning into a TISBL. So what we're turning into a TISBL is we're going to turn hotels. Now, there's a problem with this. The problem with this is we need to give it an index, and that's the reason we look at the head of it rather than look at the full thing. Month right now is not the right class either. We're doing this the long way. When you go to hotels right here, you'll go to month, and you'll see it's a character vector, which means we should take this, and let's go right here to hotels. And with hotels, we're going to go here to mutate. And now we can go year, month, and we will mutate this. We want to store this as index. I'm going to call it, sure, index equals year, month on month. Let me run it. There we go. And I wonder if we should be able to overwrite. Let me overwrite and see if that works. There we go. We overwrote it. That's good. We're going to take right here and overwrite this right here. I like to do mine in steps. It's mad because I put a space right there. This is storing on the other side of it to get that right there. Let's go relook at the head of it, which is the first 3 rows. And it's going to look the same, but when you check the class of the month right here, you can see it's now year, month class. So this is a different type of vector inside of our data frame. But now that we have this mutated right here, we can go to as Tisbel, because the Tisbel needs an index. An index is how we time order stuff. So we need to take right here and take our hotel data set and then go to index. And with index equal to month, we should be good. It should like it. No, month is not that. Month is it's an object inside the data frame, or a vector rather. And it likes it. There it is right there. So we probably want to call this something like hotels time series. And now we have a hotel time series. And the reason we do this, and this is kind of a start for the assignment, I might come back and do some more later. I know there's a question on question 3. I might take a look at that a little bit later here. But why do we do this? Well, once we have everything created right here, we can take and we can easily auto plot stuff. This kind of opens up a bunch of features. And wow, if that is not seasonal data, I don't know what is. There's some sort of odd portion right here where things go a little bit haywire, but we can look at the seasonality of it. And this is pulling the vector from rooms nights originally. You can see the increase. I think this is increasing monthly. Let me go to GG subseason, and this will look at the yearly increases right here. So this is over each year what we see, and you can see that random dip. But you can see where the monthly patterns are the highest for the rooms. We could also switch to the other vector inside the data set for the revenue. And we just need to go here. Would it be okay if we mutate, like hotel time series has 4 columns? Yeah, you could do that. You wouldn't need the original. I mean, it's just the 10,000 ways of doing stuff. So yeah, it's whatever you like. There's so many ways of doing it. It's all about what way you choose. Wow, revenue. I mean, this looks like a sort of decomp right here on revenue, some sort of multiplicative series. But this is what we're going towards. And this is what we want, the skill set we want you to have with this cumulative assignment. Does that make sense, Colton? Is like, we want you to have a skill set where we give you a data set. You know how to turn it into a Tisbel. You know how to look through it, see what issues there are. But this is kind of the start of the assignment. So we'll put like a note like starting the assignment right here. BS 475, starting homework, starting cumulative assignment. Awesome. And we'll come back, maybe do a little bit more. Starting cumulative assignment. Good stuff and good place to start. We have Canvas content next. So let's do a Canvas content and then do more 201. I mean, we're doing 201, but we got this. Oh, I need help with the Canvas content. I need help with the Canvas content. Who's going to be my Canvas content help right here? Surely we have people in the chat ready to do Canvas content. Who in the chat knows how to do Canvas content and can help me out? Canvas content. And Canvas content number 8. We haven't done that today. Where is the Canvas content? And let's preview it. I did mine. Oh, you got this, Leo. Canvas content 54, 38, stat 201, Canvas content 8. Let's do this. Okay, so this is a great review of the topics. Remember, these are test questions, so I'd write them down and I'd practice them. I would know them. Which of the following would you not check the nearly normal condition with? So we were reviewing this earlier. We were doing chapter 14. Check out the earlier portions of the video. But which of these would you not use the nearly normal or not check the nearly normal with? We have a goodness of fit test, a normal probability plot, a histogram, or a bar chart. So just make sure you have these. Like, you can just be like, psh, it's this. And we got some hints I can show you. So which one do you think it is? And there's hints on the screen. So why would you pick this and say we would not check it with it? We should really bold and underline not. Which one of these would you not use? Goodness fit, normal probability, histogram, bar chart. The answer that you would not use is you would not use exactly, Leo, another 100 points right there. You would not use bar charts because bar charts are categorical. Bar charts are categorical, and you can see up there in the top right corner, we're talking all the way up there. Bar charts are categorical. You would not use bar charts. Histograms are quantitative. And once again, we were talking earlier about the 3 ways to check with normal probability plot, with look at the histogram or look at the goodness fit test. Those are the ways to check they're nearly normal, and all these are good ways except for bar chart because that's categorical data. Which of the following is not a requirement for testing means? Once again, this is a not requirement. So when we think about not required, remember how we do our conditions? We always say condition 1 about 10 times a day. Condition 1 is random, so that's good. Condition 2 is less than 10%. We're good. And Shehzad, another 100 points. Success failure, because that's for what also? We were just talking a moment ago. Put a CRQ in the chat. But when we pause and we try to figure out the third condition, success failure is only for this kind of data. Success failure is only for... Oh, we've been doing some chapter 14 quiz. We're going to go back and do some more after this. Success failure is only for what kind of data? Success failure is only when the data is this. It's like, well, we're testing the mean, and means are quantitative. So if we're testing the mean is quantitative, and then we have nearly normal. Success failure is only for categorical data. So make sure to have that note. Success failure is only when we're testing categorical data. Nearly normal is for quantitative means. Third condition right here. This one wants us to figure out the margin of error. And a lot of times people get to this test question, they say, well, I don't have the right notation. But I think you know how to find the margin of error quicker than you realize. Your friend tells you they will show up between 340 and 350. 330, oh, whatever. 330 to 350. What is the margin of error? Just tell me, solve this for yourself, and just remember how you figured this out. Your friend says, I'll be there between 330 and 350. What is your friend's margin of error for the interval? Your friend says, I'll be there between 330 and 350. What is the margin of error? And we're going to see how to solve this and realize that we know how to do this. You don't want to... Memorizing formulas is great, but then if you realize how you're solving it, that's even better. If you're like, oh, the margin of error is this. So what are you doing to solve this, and who knows the answer? So what are you doing to solve this? Your friend says they'll be there between 330 and 350. What is the margin of error? Ooh. Exactly. So, Leo, you got it, Leo. 100 points again. What is the answer to the margin of error for this? What is the margin of error? So what is the plus or minus on this? And we're drawing it out here visually. So it's quicker than we think. And Leo's showing it mathematically how to do it. Great job, Leo. It's 10 minutes. Exactly. Plus 10 minutes. So like 340. So we could rewrite this 340 plus or minus 10 minutes. So Leo's saying it's half the length of the interval. Like, how far are these numbers away? So we would take the big number minus the small number. That's how far they are away, and then divide by 2, and there's half the length of the interval. So these numbers, the half the distance between these numbers is this. That's the margin of error. The center of the interval would be the number between them, the average of the two. The success failure condition, do we need at least 10, or what do we need, at most 10 or at least 10? At least or at most? Pretty easy question. You get this on test, you're like, boom, got this. Do we need at least 10% or at most? This is success failure. Be careful, it's not the 10% condition. At least 10 successes, at least 10 failures. Exactly. The 10% condition is do not sample more than 10%. That's the less than 10% condition. Be careful, Shehzad. Good practice. There's 3 conditions for categorical data. Condition 1, randomization. No, Shehzad, more points than that. Shehzad, I'm 3,500. Just be here to practice. We got this. The 10% condition says do not sample more than 10%. I think that's where the confusion is. But the success failure condition says we need at least 10 successes, at least 10 failures. And then the 10% condition is do not sample more than 10% of the population. So that's usually where the confusion arises. Remember, condition 1 is always randomization. Condition 2 is always sample less than 10% of the population. And then condition 3, if it's categorical, is success failure. And that's we need at least 10 successes, at least 10 failures. Decreasing the sample size will make the margin of error a smaller smaller value. So we can look at this mathematically. This might be what people were asking about. So y bar plus or minus t. Margin of error is everything after the plus or minus. You're welcome, Shehzad. Margin of error is everything after the plus or minus. And so if we decrease n, if n is smaller, think about this. If you collect less data, you'd have more uncertainty. And mathematically speaking, making that value smaller makes the interval bigger. So if you get a smaller sample size, you'll have a larger margin of error. So let's look at the question. Decreasing the sample size will make the margin of error smaller. False. Decreasing the sample size leads to more uncertainty, larger margin of error. Just mathematically and theoretically speaking. And that should be another 100. There we go. Heading back to the main screen. Let's do it. Okay, put those questions in the chat. If you are still here, we've got a lot more to do. I think a lot of people are asking about the hot dogs question, but if you have a question you want to jump the line, remember, if you're here and you're asking the question, we jump the line for questions sometimes, especially if we have it in the queue for questions, and you're like, hey, could you do this one? If we've already done it, we'll mark it and say, oh, we've already done it here. But if you're like, hey, Brian, could you do the cookies or the shoppers or the technology? Those are the ones we got in the queue right now. We're going to get hot dogs loaded up right here. Bags of cookies. Well, guess what? Cookies just jumped the line. Shoppers, please. We got cookies and then shoppers. We're doing those in that order. Cookies and then shoppers because you're here and you said it. Okay, let me get the cookies and shoppers up. Thank you so much. More votes for another. Could you do the Hoping to Lure shoppers? You got it. We'll do the shoppers and the cookies. Cookies was first and Country Club. We'll try to get to Country Club here. So remember, follow along, help out. And answer everything we can. So help me out. I get stuck on these questions. It's the 1,000-chip trial question I'm looking for. 1,000-chip trial. 1,000 chips. There, I just saw the shopping one. Luring people downtown. Oh, we're gonna do that later, Parker. Thank you so much, Parker, for asking. I'm gonna post a video for that. I'll send out an announcement in the Discord and such. Where's the 1,000? There it is. 1,000-chip trial. You're welcome, Parker, and we'll be doing that here in a little bit. You didn't say thank you. There you go. You're welcome. Okay, here we go. 1,000-chip trial. Here we go. Let's do it. So this one gives us the data. We're going to try to do as many as possible, so help out in the chat. Okay, so we have 10 observations from bags. So you're literally, this is a long thing to do. You're grabbing these bags of cookies, and you're just ripping them open, and you're counting all the chips in the cookies. They claim that these cookies have 1,000 chips. It's Chips Ahoy, basically. And that each bag will have 1,000 chips in it. 1,000 chips. So let's take our data, have jump open, and let's go here and go to copy to clipboard. This will copy the data for us, making our lives a lot easier. Now that we've copied to clipboard, we should notice there's no column name right there. So when you hit Command-C or Control-C, Mac versus PC, make sure when you go into jump and you go to File, New Data Table. We'll pause right here. Go to File, New Data Table. Anywhere in Jump, you'll see it there at the top of the screen. File, New Data Table. Boop. Make sure to go to Edit and then Paste. You can actually just paste normally. There was no column name, so we don't have a word at the start of it. It's just going to paste normally. Do not paste with column names or you'll put the first observation in the column name. So just paste normally. Just edit, paste. You can literally just hit Control-V if you want. Sometimes you do have to paste with column names. Watch the other examples or check to see if there's a column name. Now that we have the cookies in here and how many chocolate chips were in each cookie bag, we're going to go here and go to Analyze Distribution. This lets us analyze univariate quantitative data to see the distribution of it, to make confidence rolls, and we can do statistical tests on it too. So Analyze Distribution, double-click the Y variable of interest. Oh, the nutrition? Let me know, Brent. Oh, and I still have... Kristen messaged me. I need to look at Kristen's message. Message me, Brent. I'll take a look. I'll try to catch up on everything. Weekend was a bit busy. It was a busy weekend. And so we got this right here. And we'll just go ahead and click OK. And a little bit of a weirdness to the histogram. We're going to click up here to the top and click Stack. Once you click Stack, it's going to go into horizontal layout. Boop. And let's go take a look at what we got for the question now. Okay. So it asks first about the conditions for the test. Are the conditions met? The independence condition. The data are randomly sampled, which means we're probably good. The data from a random sample, so we can assume they're independent. We just call it the randomization condition. Sometimes my Pearson wants to talk about it as independent, but if it's random, you're good. You can just check to see if it's randomly sampled. Random sample means they're independent, because if they're not independent, they're not random. So if they're random, they're good. Now, here's where you can actually deduce the right answer. Our histogram looks a little bit weird because bin widths. And what do I mean by that? Well, the histogram we made doesn't look like any of these. If you double click here, you'll notice that it starts at about 900. No. We'd have to look at the shape, Chase Odd. No, that's false. Because if it's very skewed, we'd need a very large sample size. That's large enough N right there. So if it's very skewed, we need a much larger. That's large enough N condition. So that'd be false. The parent population, if it's very skewed, would need a very large sample size. False. Good question, stays odd, 100 points. You're welcome. And so here we're going to go from 900 to 1600. Notice the lengths right here. And we're going to remove the tick, and that's what you want to do. If you do this, you'll get the following. If you notice, it looks a lot like this. If you put 700 to 1400, it would actually be off the screen a little bit. It'd go down here and to 1400. So it would look like this if you accidentally put in the other numbers. So it's not going to be centered properly and say, oh, well, that's more centered at about 900. And once again, this does look, I mean, they're giving you as normal can get right here. We did the flights. We didn't do the garage question yet. The shopper downtown, lowering shopper downtown. We probably can get to that, Jalen. Good question. So that's our histogram. There's our histogram. Evaluate the histogram. Histogram looks unimodal, symmetric with no outliers. Let me see, make sure I got it. Oof. This one gets me. I had to restart this test. Oh, sorry about that, Brent. Yeah, that's weird. I don't like that. Okay. With no outliers. Okay. This one gets me. This one I get mad about. There's a 50-50 shot Brian will miss this question. And if you miss it, email me and I'll correct it because I don't think this is fair. We're going to use the t distribution, but I'm pretty certain they have you say that it follows the normal model. But that's the condition. The condition is the nearly normal. And the t is an aggregate of the normal. So it's almost like... It doesn't matter! We are using the t distribution. Oh, it's just the population. The t is how we model it. We think that, yeah, I think that's why. I think that's the theory part that I must have never read about this question properly. The data come from a population that's normal. The population wouldn't follow a t. The population would be normal. We model it and try to understand it with the t. So we model it. I think that's where they're going theory on it. Like, my Pearson's probably being very particular on that. That the population is nearly normal, hence the condition nearly normal. The population isn't t distributed. The t is how we model it. William Gossett with Guinness beer. Okay, teaching the test moments. So now that we need a 95% confidence interval, we can go right here to our 1186.0304. One decimal. Oh, rock. It doesn't matter, man. 1186.04. 1186, right? Please tell me if I'm entering these in wrong. My brain's 1186, 1353.6. Let me double check. Always look at these. We are on a streak today. 1353.6. There it is right there. 1186. And that would round to 0. 1186. Okay, I don't think we have any errors right there. What does this say about the companies? Now you have to be very careful right here because we're not talking about all bags. We're talking about on average because we're estimating the true mean, which sometimes it puts mu between the interval. So we would say I am 95% confident. This is 95, yep. I am 95% confident the true mean amount of chips per bag is contained in the interval 88.86 or 11.86 to 1353.6. And that is the true mean. Now, it could be possible that some bags have less than 1,000, but we think on average, the true average is higher. So companies write about the average amount, but it could be possible that you could get a bag that has less than 1,000. So because the confidence interval is entirely above 1,000, this means that the number of chips per bag, because the confidence interval, no, it doesn't include. Because the confidence interval is entirely above, this means that the mean number of chips per bag is likely more than this. However, the normal model predicts that a small amount of individual bags will have less than this. This doesn't mean every single bag will have more than it. Correct. And yeah, I think I finally realized why they're saying the population follows the normal, and that is checking the nearly normal. So I'm sorry, Matt Pearson. I should read your answers more carefully. You're being very particular, as we are as statisticians. Let's do some more problems here. Here we go. Ooh, sometimes Brian needs to slow down his mind a little bit. Sometimes Brian needs to pause and think about those problems. The next question that students wanted, and make sure we've got shoppers, hot dogs, and technology here. We've got cookies on the, we know we just did cookies. So we got shoppers next, hot dogs and technology coming up. But if you're here, you can say, hey, wait, do this one. Oh, is it technology to get the T statistics? Ooh, I do like that one. And I need to send out an announcement. But if you're here, let me know which ones you want. Assignment 10 for BS3. Oh, yeah, a 1A? Oh, Parker, let's see. Parker, let's try to do that. Parker, I'm probably going to put that one in here next or after this one. Parker, thank you so much. So that's Logistic Assignment 1A. People are saying shoppers. So people want shoppers next. We're going to do shoppers, and then we're doing logistics. Parker, you're here, and we haven't done a single BAS through 20. Thank you, Parker. So we put that next after the shopper question, hoping to lure shoppers downtown. So we're going to try to do this one quick. Join in the chat. Thank you, everyone, for being here. And Parker, your questions come up next. Thank you for being here, Parker. You're welcome. We make a list of questions, and then we give priority if you're here. So if you're watching this in the future and we didn't get to your question, swing by office hours. We try to do as many as we can. More interaction, more we do, and we add all the timestamps in. There we go. Timestamps ready? Let's do this. Okay, hoping to lure shoppers downtown. They're trying to figure out this public parking garage. The city plans to pay for the structure via parking fees. They take 42 weekdays. They find out the average was 133 with standard deviation of 14. Channel Leo right here. What are we going to do? First thing we're doing right here. What are we doing first thing on this problem? This one's a little bit different than all those questions we've been doing previously with jump, because now we need to practice our what? Who knows for 100 points? Notation, brother. Right here. Leo's got it. And you know what? Today's your lucky day. Today I'm going to help you out with the notation. Take a pause right here. See if you can get the notation for this problem. If you have your formula sheet for the test, you'd be looking for y bar plus or minus t with n minus 1 degrees of freedom. That's the degrees of freedom, which tell us which t we are using, s over square root of n. So when we do this, we need to find the sample size, which is 42 days. We need to find the standard deviation, which is 14, the sample mean, which is this, and then usually people get stuck here on the degrees of freedom. The degrees of freedom are n minus 1, so the degrees of freedom here are 41, and that tells us which t we are using. Now, whenever you do the t, it's not consistent. Great job, Leo, there on some 41 degrees of freedom. And now we need to go where, Leo? Where do we need to go? The assumptions... No, we don't want at least 10%. The data random... Yeah, you don't want them to be dependent. You want them to be independent. That would be random. And you want less than 10%. So now we have to go to the t-applet thingy, correct. And notice how it says, so we marked all our notation. We'll solve it here in a moment. Notice how it says we need to make a 90% confidence interval. So when you go to the t-applet thingy, you want to go over here to this page. You want to enter in between two values. So you're going to get the between and do 90% on it. And now you need to enter in your 41 degrees of freedom. So make sure to enter in your 41. You might need to reload the page. Someone was saying there was an issue with that. Make sure it shows you the following where you have like 90% between two values and your degrees of freedom found by n minus 1 for the one sample t. There's the degrees of freedom, which tell you which t you are using. So this is basically the z-score we've been using, but it's a more exact calculation. So by going to the t-applet, not that one, we have this one right here, we can see that the t-score is 1.683. 1.683. That is the proper t-score to use. And I prefer applets because you can get the exact number and everything should work out nice and neat. Fingers crossed. Okay, so let's go check this out. We're going to plug in the numbers right here. The sample mean was 133. That's a lot of money. Plus or minus 1.683. The t-score we found, that you don't times by degrees of freedom. They're just a thing to tell you which t you're using. 14 over square root of 42. First thing I solve for is the standard error, which is s over square root of n. So we're going to go over here. After this, could do the... Yeah, we did some technology. Yeah, we're going to do Parker's question next. I bet we could do technology. Someone else was asking that. So there we go. There's the standard error. I just solved for 14 over square root of 42. Now I'm going to times that by the t-score to get the margin of error. There it is right there. There's the margin of error. So 133.364. We're going to make sure we cover everything. 133 plus or minus and 3.635. There we go. So there is the interval plus, or the center of the interval plus or minus the margin of error. And let's go ahead, and we've got the number right here. That's our margin of error. So we go 133 plus that. And it says to 2 decimals, so 136.64. And then we get 133 minus that. I've got it in my copy paste. Just make sure to copy paste it. Makes life easier. 129.36. And that should be good. Explain what this means. I am 90% confident that the mean, I think right here, this looks accurate. I'm a little worried on this. Let's see. I am 90% confident the interval contains the mean daily income. That sounds right. There is 90% confidence that the mean daily income will fall. This is a very particular thing also. We don't like to say that the thing falls in the interval. I'm going to get really mad if that's the right answer. But as statisticians, the active thing is on the interval containing it. If you look at my interpretations, I am blank percent confident that the true blank is contained in the interval. That puts the active word on the interval. So they're being very particular on the value is not going to fall in the interval. The interval would contain the truth because the truth exists. We don't change the truth. We are making an interval that might contain the truth. And if they tell me I'm wrong, I'm going to be super mad. Explain what 90% confidence means. 90% of 90% confidence intervals will contain the truth. So we need something like that. 90% of all sample sizes of 42 will produce intervals that contain the truth. So 90% of 90% confidence intervals will contain the truth. And that's what a 90% confidence interval means. Since the 9% confidence interval, what does it say? They're saying, what are they predicting? They predict 140. Oh, that's not in there. That's way outside of it. So since 9% confidence interval does not contain that, the consultant prediction is not plausible. Woo! We're on a streak today. No questions wrong. That's how we roll. We'll come back here and do the technology one next. Let me send an announcement to the class with the 30 minutes till class time, and we're going to do some 320. A lot of work today. Here we go back to the main screen. Let's do this. Thank you so much, everybody. Class coming up here for the next class. We're sending the announcement to their class saying, class coming up. So if you're in class, make sure to hashtag show up because it is busy. Woo. Where is it? Oh wait, class playlist. I confused myself. Maybe I should put the class at the top of the list. Got 2 people watching. 2 people. Class in 30 minutes. See you soon. Click here. Okay. Make sure the link works. Good stuff. Send announcement. Now let's go grab 320. Super Saiyan chat. We did the chips. Yep. The chip trial was done at 1 hour mark in. So I think it was the one right before this. Rewind about 20 minutes and we did the 1,000 chip trial. Morgan, thank you for being here. Morgan, 100 points, Morgan. We did the 1,000 chip trial about 10, 15 minutes ago. Rewind a little bit, you'll see me doing the 1,000 chip trial. You can actually rewind the video live if you go down here. But check out the 1,000 chip trial. We can do a little 320, and then we got the technology ones next. Let's see all here. Need to make a video for that later. Logistic regression. Okay. And Parker was wondering about the start of it, right? Here we go over here. Let's start up. Country Club, I might have just enough time, Cassandra. Let's go. Okay, so this is 1A on logistic regression. So we need to make sure we have the data, which I do not have. Let me go get that. That's the environment we need. Okay, data file downloading. And with the data file downloaded, it works. Make sure it's in your working directory. And so now we have the data file downloaded. We probably have just enough time, Cassandra. We're going to get a lot done. So now the first question asks, use homework 10 donor. Let's remove out everything. We got Titanic data. Ooh, Titanic data. So let's load in just the homework data here. There we go. Use homework 10 donor. This is a modified portion of the donor data set. It deals with the charity, blah, 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 blah. Each row is an individual. Here we can see data on them, whether they donated or not. And let's take a look right here. So we've got how much they donated, their last amount, whether they donated, the account age, the individual's age, whether they're from a rural, urban setting, all these different variables. It looks just like JUMP where we have categorical data, quantitative data. So a lot of JUMP 201 crossover here. All this good stuff. A logistic predictor of somebody's last donation amount is the average amount he or she donated in the last few years, recent average. However, the strengths of relationship may depend on various levels. Let's first explore if gender of donor is a good predictor of donate. So build a model predicting last amount using the variables recent average amount and gender and their interaction. Now, here's where the mistakes usually happen. Good to see you here, Jameson. This is different. This is a great example for office hours because when you're doing this, we'll no longer use LM. For 500 points, does anyone know what we need to use instead of LM? I'm going to write this out mostly right here, and I'm going to make my life easier by going attach, doing things I shouldn't do, and go to donor. And instead of using LM, what do we use? GLM, KP, great to see you here. What did I say? I say 1,000 KP joining in. KP, you are right. We use what's called the generalized linear model now. So the G in front of the LM stands for generalized, and I'm attaching it so I can do autocomplete. We are predicting donate, and notice how it autocompletes because I did the attach. That attaches vectors to the global environment, gives you the autocomplete function. We want to do recent average, and then we want to do the interaction with gender right here. There's gender, and then you have to do another thing. So let's go data equals and homework 10, and then last but not least, family equals binomial. If you don't do family equals binomial, it actually does Gaussian, which is which is linear regression. You can see right there where it says family equals Gaussian, and that's the type of regression you're doing. So Gaussian is linear regression, so it will do linear by default. You have to tell it family equals binomial, and then you will get logistic because binomial, like two-level categorical. And this is because we're predicting a categorical way with y with the probability of it. So by doing this GLM right here, we store it into the model. That's fine. Warning message. You can actually make that go away. This is not a big deal, but you can go suppress warnings. I don't like warnings. Oh, look, no warning. We just suppressed them. So now, that's just an additional thing you can wrap around it to stop warnings from appearing. It doesn't matter. Thank you, Rock. Let's go ahead and visualize this and see what we got going on right here. Visualizing the model. Ooh, really? That's weird. Something weird in the neighborhood. That's weird. Is that the right model? Building model predicting last amount. Oh my gosh. What have I done? We're predicting last amount. We are predicting last amount. I went too quick. There we go. There we go. There's no interaction on that. There's the no interaction. Yeah, actually, KP, you are right. Brian went too quick. Hey, Priya, great to see you here. Sorry, my brain was going thinking logistic because last amount is a what kind of y. We do use LM here. Now, if we predict donate, which we'll do later in this assignment, we'll use GLM. But why are we using LM right here? This is good. This even relates to 201. Why are we using LM right here? Why are we using LM? Think about what last amount is. Why we're doing linear regression, which is LM, linear model. It's a linear model. Exactly. It's quantitative Y. I read it way too quick. Could you do technology and golfers? I think we're doing technology next. We might. And then we'll do the other one that what was it, Country Club Cassandra was wondering about? I think, yeah. We probably might have just enough time to do both. Might. We'll find out. Yeah, no, KP. Already submitted? KP, great work. Yes, you did it properly. I did it wrong. Hopefully, sorry anyone who's watching this. We can look at the summary of this. You can see that the interaction is not significant. And I do want to point this out if you're watching this. Notice the p-value of the interaction right here can be found. Now, this is the full interaction. If you had something like setting, which this doesn't ask for, but if you had setting in here and you looked at these p-values, this is not the p-value of the interaction, but you could do either the drop one or visualize your model to get the p-value of the interaction. It'll do the effects test drop one. So have you gone over? We did chips about 20 minutes ago. Great question, Priya. We did the chips about 20 minutes ago, and I'll probably add the timestamps to this video pretty quickly. I need to add them in more quickly. But we did 1,000 chips about 20 minutes ago. Is this making sense right here, Parker, on what to do for this? I've changed the question up a little bit, but how to make the model, use the variables it asks for, and go through, is it a good predictor? We need to look at p-values to see how to tell that. Should the interaction be included? Look at p-value of the interaction. I've got a different thing up, but look at p-values of the interaction. And then we can look at some other stuff, home motor being a good predictor. But does that make sense on how to go through this, make the output and make the model? What are you thinking? We're going to go back here and do the technology question next. But 320, what are your thoughts? We're going to do the activity coming up here a little bit later today. We'll see what chat says. I'm going to over and do the technology and country club. Where's my music? I think it's time. Hey, Madeline, good to see you here. We've been doing a lot of the chapter 14. So get ready, more chapter 14. Here we go. Good to see you, Madeline. 100 points in the chat, Madeline. We've got technology questions. Now, I need people's help for this. Where are you going to go when it says use technology to find the answer? Let's go check it out. The technology questions, technology finding T. So we're going to take this right here and go to... Oh, no. Did we not do timestamp on that? I'm taking a guess at that. T thingy. Yep. Exclamation mark T. Drop an exclamation mark T in the chat real quick for me. Anybody for 100 points. Drop an exclamation mark T and Mubot will send us over to the T thingy. So we're going to do the technology right here. I'm getting the timestamp. Oh my gosh, Leo, you rock. More people dropping T in the chat right there. You thought T was drama, but no, it's technology. So, chapter 14, finding T with technology. All right. Okay, let's see. We took a little bit of time right here. Let's go do it. So what's interesting about the T statistic is the T is basically the Z. Mr. T comes in, he smashes down the curve, says, I'll pay the fool, smashes it down. And the more freedom he gives it, the more normal it is. So the T will approximate the normal, the more degrees of freedom it has. So it actually, when you have a 95% confidence interval, usually the Z-score is 1.96. You might remember that from other chapters. The T is dependent on degrees of freedom, so you have to know your degrees of freedom to know the T. But the T and the Z kind of converge, which means at this point, the T is basically going to be this right here. And 98% is 1.3263 Z-score. And then that means the T-score is probably about 2.42. Check answers. 50%. No. There we go. Now we got 100. But let's show how to find this. I don't use the two-tail for it. I'll show you which one I use right here. The T approaches the normal as it gets more degrees of freedom. I'll show you how I would find this with technology. Let's go over to the T-applet in the chat. And notice how we have degrees of freedom. And also I select this one right here. So I select the one where we plot the middle percent. Now, the first question we had was 98% confident. Make sure it shows the 98. Exactly. It has a narrower center and fatter tails, and you can see it right here. Look exactly what Grace is saying. 100 points, Grace. Grace is telling you that the T has a narrower center, and you can see it right here, narrow in the center and fatter tails. But as you give it degrees of freedom, it goes towards the normal, which has the 68, 95, 99.7 we've all known. But when it doesn't have freedom, it's like that. More freedom, more normal. So I actually make guesstimates based on that. You have to know the degrees of freedom, though, like 28 degrees of freedom, to put it in here and find out 1.47. And I think that's exactly what I guessed on my second guess. 2.47, excuse me. And then 95% confidence, change this to 95, and enter in the 61 degrees of freedom, and then there's 2. So it's very close to 1.99, and I put 1.99, but it's basically 2. Now, if you give it a lot of freedom, it'll go to 1.96. If you give it very little freedom, it's very different. So these are good questions to understand where the T value comes from. It comes from the T curve. I think there's one more right here. Now, this one is very easy to guess because I know the answer for the Z-score. Since I know the Z-score is 2.5758, I can basically guess this, and that'll be right. But this one is nearly impossible for me to guess because it's so... Does that make sense, Grace? I'm hopefully giving a bigger understanding than just plug the values in, because you can just plug the values in and get the right answer. But because the degrees of freedom are so small, the curve is very different from the normal. Does that make sense, Grace? Like, this one is very hard for me to guess because it's going to be very different from the Z-score. That's 1.645 as a Z-score, but the curve right now is really smashed down. And I'm like, okay, it's smashed down really far. It's going to be like 1.92. Oh, I didn't get either right. Wow. There we go. I got that one right. This one is just very hard to guess because, yeah, and we'll find out the right answer. So if you want to really get the right answer, other than guessing it, I was shocked I got the other one wrong. You need to go here to the 90% and enter in 7 degrees of freedom, and it's 1.90. I think I was in the ballpark of that first guess. 90%, 7 degrees of freedom. And you're not meant to guess these. You're meant to go to the applet. It was that one I was like, when I got it wrong, I was like, it's that one. Because the bottom one right there, I'm surprised I was even wrong on the 99. But that's basically the z-score of 2.5758. The z-score is consistent. The t-score is based on degrees of freedom. But the t-score will approach the z as it gets infinite degrees of freedom. So this is the knowledge I'm using to solve when I'm doing the quick solves, is that I know for a 99% confidence interval that it's 2.5758 for the z-score, because if it has infinite degrees of freedom, it'll approach the z. So when it said like 107, I wrote about what it said degrees of freedom, I knew I had to go a little further. I was like, get the hiccups, 106. And that's going to be basically the same because it's the same degrees of freedom. We didn't even see a decimal change right there. But hopefully people are following along that the t and the z are basically the same. And as the t gets more degrees of freedom, it approaches the normal. But when it has less degrees of freedom, the t is more squashed down. And as Grace was saying right there, it's more narrow in the center and has fatter tails. But when it gets degrees of freedom, it turns into the normal. And that's why I can more easily guess it and answer high or low. Brian has an easier time guessing the answer when the degrees of freedom are high or low. When does Brian have an easier time? Because that means you probably understand what the curve does. When does Brian have an easier time guessing the t value? When it has a lot of freedom or when it has very little freedom, degrees of freedom, which I just call freedom at times. When does Brian have an easier time guessing the answers? When it has a lot, high degrees of freedom. Yeah, because at that point, I'm just using my knowledge of z-scores. Exactly. Mubot, you're crazy, man. Because it's basically normal. It's basically normal. A lot of tables will just put the z-score for very high degrees of freedom. Like, and a lot of times people might even just use the z-score for very high degrees of freedom. But technology will calculate it more finely. Like if you're over here on the Apple and Blue Country Club next, if you do like T norm, no QT, so the percent 1.96. But if you go here to Q norm, and that's exactly down to the decimal. There, go look. So this is for 99,293 degrees of freedom. This is the t-score, 1.96 basically. See, people aren't even using the z-score exactly. It's not 1.96, it's 1.959964. And then you could take more decimals. But the numbers converge after a while. And frankly, after about 200 degrees of freedom, it's probably not a big deal. It's 1.97 there. But if you go to more degrees of freedom, it'll just start to approach 1.96. It'll just keep going towards 1.96. But the problem is when you have very little degrees of freedom, that's when you'd see a big divergence from it, which then I don't know those off the top of my head. I'd have to use an applet or technology to get them. Some people use tables. I'm not a fan of tables. Made me fall out of my chair right there. Tables, no. You might say, Brian, why not tables? Well, tables are just a bunch of numbers written down. And there's so many different confidence roles, so many different degrees of freedom. Technology can just find the answer like that. And a table, they have to write down all the numbers. And you're just flipping through pages. And I've seen big t-tables with tons of stuff. They're like, oh, this t-table has all the numbers. So I'm like, I can just punch in the numbers and the computer can tell me the answer. So I'm a huge fan of technology. You never would have guessed that from me. Brian likes technology.
Wow.
Let's do the country club question here to round off. We've done most of the quiz today. We did other ones. Country club question. Here we go. This one's going to be a solve the interval by hand problem. Country club question, go. Okay, I'll take the timestamp here. Country club question. Do we delete it? Stat 201. Country club. Chapter 14. Country club. Okay. So you know it, Leo. You know what we're going to do. We have instantaneously right here some notation. So with the notation right here, we're just going to go ahead and grab it and bring it over to here. Now, we need to know all the notation. And we need to know the symbols for it. When we see count, that's sample size. We see mean, that's y bar because they took this from a sample. When we see standard deviation, that's s because it came from a sample. Make sure you know that these are sample means and sample standard deviations. Now, one thing you don't have from this right now, or didn't tell you, is the degrees of freedom. The degrees of freedom for the one sample tier n-1, which means it's 201. When you know the degrees of freedom, check out the previous problem. That means you know which t-curve you are using. The t-curve you are using is the distribution which will get you some of your answers. It lets us know the t-value for the confidence interval, and we can go over here and put in our 201 degrees of freedom. And then we are going to build confidence intervals, so we go between, and we might be building something like 90 or 95. We'll check out what the value is here in a moment, but make sure to put the percent confidence between, should shade the middle area, because you're doing between this and this value, like 95% confident, lower upper bound, and then make sure your degrees of freedom are the correct degrees of freedom, n-1 for the one sample t. So now it wants 95% confidence, good, and let's go ahead and solve this. Now, this is where you have to use technology or t-tables, not a fan of those, but you could if you want. And we have that's 95, no, wrong value. 95%, 1.972, close to 1.96, but you have to use the 1.972. So this value here is the t with n-1 degrees of freedom is 1.972. That's subscript for the degrees of freedom that we're talking about up here. And now we have all the values we need for y bar plus or minus t with n-1 degrees of freedom. The star means you get to pick it based on confidence level, and s over square root of n. So we're just going to plug in our numbers right here. The sample mean is 285.1 plus or minus the 1.972, and then s being 9.2 and over square root of sample size. And remember how we solve this. The first thing I solve for is my standard error, which is the last portion right here. So I take 202, square root that, and then I take 9.2, divide by it. That's the standard error, this component, times by 1.972 gives me the margin of error, and we basically have our answer once we do 285.1 plus or minus the margin of error. So 285.1 plus or minus the margin of error of 1.276. There we go. And that looks to be the answer. So we're going to take the margin of error, we're going to copy it and do 285.1 plus the margin of error. So 286.4. And then we take 285.1 minus, and that's 283.1 decimal, so 283.8. Come on, brain. You got this. Okay. The conditions, what is the problem with this experiment? Oh. So the problem with this one is they're doing, hey, Brian, hey, Colin, great to see you here. If you're wondering about my weekend, I had a big weekend, Colin. I don't know if you heard. Thank you so much, Colin. Good to see you here. But I had a big, exciting weekend. So big, crazy weekend. So not crazy, but good. The histogram, it only chose the top golfers. We need to randomly select. The data are the mean driving distance for each golfer. Is that a concern in the interpretation of the interval? Definitely. Oh, thank you, Colin. 100 points. These are very accurate. Yeah, exactly. Leo knows what's up right there. The data are the mean for these golfers. Is this concern in terms of interval? Yes. The mean driving distance are less variable than the So it's the mean for each, and these are sample of the tops. Woo! Getting scared there. Let's see. Which ones did we not do? We could do a little speed run. I think we basically did all the big ones. We didn't this one. We didn't do the hot dogs. This one uses let's just mention the other problems. We'll just say mentioning other problems. So 140, because we got class in 10 minutes. Oh my gosh. 140, 25, stats for one, remaining problem. Problems tips. Okay, so this one right here gives you the summary statistics. This is the same way. Make sure to go to your applet, get the numbers, but this one is the same format as the ones we were previously solving just moments ago. where you're gonna, can we do, oh, we're gonna do the activity later. The assignment, swing by Audrey, we're gonna do the activity, or tomorrow we could do the question. I've got 9 minutes till class. So Audrey, thank you so much. We did a little 320 a little while ago, but we can do it tomorrow. So Audrey, thank you so much. We'll definitely try to do it. I'm gonna grab a little food between class. So this one right here, you will solve based on the equation where you find the notation. That's a notation solve question right there. This one right here, did we not do this one? This is another notation solve. So notation solve right here. You're welcome, Audrey. Thank you so much. That's another notation solve question. This one right here is margin of error. We are 95% confident. Calculate 99%. Oh, I got the margin of error wrong. Is that not about it? I was around up? Really? What? I'm gonna like calculate the margin of error now. Ooh, did I get another one wrong? 3-0. Oh my gosh, I can't read. It's 64.8. So that's 5. No, it's 4.3. Half of 4.3 is 2.2 rounded up. We're actually going to solve this. My brain is not working. What did I just do there? What did I just do? We did the flight one earlier, Cassandra. Check it out. Sally. The flight one was done at 20 minutes into the video. The flight one, a lot of stuff today, a lot of great stuff. Oh my gosh. We lost our streak because Brian was trying to guess, and Brian guessed wrong, and then Brian doesn't know how to solve mathematics. Brian can't take two numbers and subtract them and get their difference and divide the difference by 2 to get 2.1. So I'm trying to do in my head. There we go. Half the length of the interval is the margin of error. Make sure we're just trying to give you some confidence to show you that mistakes happen. That whenever you're trying to find the margin of error, it's half the length of the interval. You're watching that right there. Margin of error is half the length of the interval. Find the length of the interval. Find half the length of the interval. Don't try to do it in your head. Solve it using a calculator. You'll do better. Just make sure it kind of makes sense when you solve it, because somehow I clicked a wrong thing. Oh, our redemption problem. You ready? We are 95% confident. If we went to a 90% from a 95%, that would be a smaller margin of error. And then we look here at the interval and we say, okay, interval, you are 4.8 in length. 4.8 half of is 2.4. Check answer. Well, 6 minutes till class. We're going to head off right here. I think that basically does it. We did pretty much all this quiz today. Good stuff right here. What would the degrees of freedom be? That's 14. Degrees of freedom -1. That's easy. Which of the following are t-distribution, unimole symmetric, have fatter tails, degrees of freedom, becomes normal. Boom. Done. I think we actually did all of them now. With that, we're going to head off right here. We'll see everyone for 201 here in just a little bit. Good work on the assignment. Talk to everyone later. Bye for now. Bye. See you in class.